In this lesson, we're going to go through the notes for section 2.6, looking at equilibrium problems. Equilibrium problems are most commonly attempted with what's called an ice table, so I highly recommend playing Ice Ice Baby by Vanilla Ice while you're doing these. It's very motivating. All right, some of the goals for this lesson is to solve equilibrium problems using ice tables. So we're going to look at a few different scenarios. We're going to try and determine in KEQ if we have one equilibrium concentration and we've got initial concentrations. We're going to try and determine equilibrium concentrations if we've got the KEQ and initial concentrations. And then we're going to try and determine initial concentrations if we're given the KEQ and equilibrium concentrations. So it's kind of like looking at a little Sudoku puzzle and trying to solve the various parts. One of the questions you may ask about this is, why do I need to do this? What is going on? Why do I have to do all this math? Well, it turns out that this is really, really important for industrial chemistry and for pharmaceuticals. We want to make sure that we're able to manipulate the conditions of an experiment so that we can increase yields or purify different samples. So it's actually got a really strong practical component, and we're going to be looking at how we can use this to make predictions. So the first activity I have here is a warm-up activity on page 129 of your workbooks. This is kind of an introduction to an ice table, and it will take you through the basics of how to use it. So I'm going to encourage you to kind of pause the video for a minute, see if you can go through the steps 1 through 5 in your workbooks and fill out that ice table to completion. So pause the video now, take a break, and then we'll go through it. Okay, so step number 1 says solve for the equilibrium concentration of nitrogen, N2. So you can see here that we started with initial conditions of 3.0 moles per liter, and then we had a change. It's going down by 2.0 moles per liter. So when we take 3 minus 2.0, equilibrium concentration is going to be 1.0 moles per liter. Second step says solve for the change of the concentration of chlorine and nitrogen trichloride using coefficients. So what that means is that we know that if nitrogen is going down by 2, it has a coefficient of 1. That means that for every 1 nitrogen we use up, we're also going to be using up 3 chlorine, because that's the 3 coefficient there. So rather than going down by 2.0, this is going to be going down by 6.0. And if you get confused there of whether to multiply or divide, we can always do some stoichiometry. We can say we've got negative 2.0 moles per liter of N2. And we're going to go over to Cl2. So I've got 3 Cl2s for every 1 N2. So you'll notice that those units, the nitrogen cancel out, and we're multiplying by 3. That's why we're going down by 6.0. So both of those are reactants. They're getting used up, and that's why we have the negative sign. On the other side of the equation, we have the products. This is being produced. So on the right-hand side here, I'm going to put a plus symbol, because as those reactants get used up, they turn into the products. And so these are getting added to. And you'll notice that there's a coefficient of 2, so that's going to go up by 4.0. With number 3, it says solve for the equilibrium concentration of NCl3. So I went 0 plus 4.0 gives me an equilibrium concentration of 4.0. And then step 4 is a little bit tricky. It involves some of our work from the previous lesson. So it says solve for the equilibrium concentration of Cl2 using our KEQ expression. So if you'll remember how to use the KEQ expression, our KEQ is equal to the products over the reactants. And we're going to take those concentrations of the products, and I'm going to raise it to the power of the coefficient. And we're going to include anything in our equation that is aqueous or a gas. So everything in this one. Okay, so there's our KEQ expression. And it tells us the KEQ value over here on the chart. So I can substitute everything into that equation. So I'm just going to do it over here on the left-hand side of my page. 0.128 is equal to, and we're going to substitute things in from our equation. NCl3, that's the 4.0 squared, divided by N2, that's 1.0. That's just raised to the first power. And then that concentration of Cl2 is going to be what we're solving for. It's going to be Cl2 cubed. So we're going to rearrange this equation to solve for Cl2. We should be experts at rearranging by now, so I'm going to kind of flip. I'm going to put my Cl2. I'm going to swap it with the 0.18. And we're going to solve for that concentration of Cl2. So 4 squared divided by 1 times 0.128 gives me 125. Lastly, I'm going to take care of that cubed. So the opposite of cubed is cube root. Cube root both sides. And my final concentration of Cl2 is equal to 5.0 moles per liter. So I can fill that in my chart. Okay, last thing that we're going to do is it says solve for the initial concentration of Cl2. Well, you can see that my initial concentration of Cl2 here, something minus 6 gives me 5.0. I mean, I can turn that into an equation if you want. X minus 6 equals 5.0, but it's pretty obvious here that that's going to equal 11. X equals 11. So there's how we fill out that whole table. So it's just kind of a problem solving, and notice that we use that change row was related to the coefficients, and we kind of fill in the equilibrium concentrations using KEQ. This is an example of what we're going to be doing today, and we're going to be looking at various parts of the table, what to do if we've got initial concentrations or final concentrations, or we know a change, or we don't know KEQ. So we're going to be looking at different scenarios of that. So I've kind of broken the problems into different categories. Category number 1 is everything at equilibrium. When we have all of our values at equilibrium in the beginning, this becomes a fairly straightforward problem, and we don't actually need an ICE table. So these are the types of problems that we were working on in the previous lesson. So it says the equilibrium equation for the formation of ammonia is N2 plus 3H2 yields 2 NH3. You should be really familiar now with the Haber reaction. In an equilibrium mixture, now you'll notice that this is at equilibrium. So we're thinking about the time frames. This is at equilibrium. It tells us our temperature, just because our equilibrium constant would change if that temperature changed, but it tells us that equilibrium concentration. So it wants us to calculate the value of the equilibrium constant at that particular temperature. So again, this is review from yesterday. KEQ is equal to the products over the reactants. We're going to raise our products to the power 2 because that coefficient. And same reasoning, I'm putting H2 cubed. So we're just going to substitute in those values. And we'll solve for the KEQ. Just remember your bracketing if you're doing this all in your calculators. And I got a KEQ value of 625. Okay, so again, review from yesterday. The second type of problem, category 1, everything at equilibrium, is we have a KEQ given. And you'll notice it's the same one that we just calculated because the temperature hasn't changed. But this time we're asked to calculate the equilibrium concentration of hydrogen. So we're going to attempt this the same way. We'll fill in what we know, and we're going to solve for the missing part. So I'm just picking out those concentrations based on what I'm given in the problem. Hydrogen is what we're solving for, so we tried this problem yesterday. With this one, I'm going to do a little bit of rearranging the equation, so I'm going to swap the 625 and the H2. And then to get rid of that cubed, I'm going to cube root the whole thing. So you can do this in one step in your calculator, or you can do it in a couple of different steps. If you're doing it all in one step, just remember your brackets. And I got a final concentration of hydrogen here equal to 0.092 moles per liter. So if you didn't get that, maybe pause the video, see if you can work through your calculations. Make sure that everybody in the class is able to get that number in their calculator. And then we'll move on to the next. Okay, for some of these problems, there's a couple of different formulas that I want to revisit before we get in here. One of the things you'll notice that is anytime we're using the KEQ, or if we're using our ICE tables, which we'll introduce soon, we need molarities in here. And so one of the formulas that you would have learned in the grade 11 class is the concentration formula. Concentration is the number of moles divided by the volume. And we usually express molarity in moles per liter. So you're going to want your moles on the top and their volume in liters. So we're going to use that formula quite a bit. Always remember to convert to molarity before using the table. So here's a category 2 table. Now we have things that are not all at equilibrium. We're given an equilibrium concentration, but we're also given initial concentrations. So we've got 2 time frames that are talked about in the problem. So the problem reads, the following gases are placed in a 4-liter flask. So already I'm noticing that this is not a 1-liter flask. I'm going to probably have to do a little bit of math just to put things in the table. I've got 8 moles, there we go with the moles, of N2 and 10 moles of H2. After equilibrium was achieved, 1.20, and now we've got a capital M. That is a molarity of the ammonia is found in the flask. Complete the ICE table and determine the equilibrium constant KEQ. So I've got 2 different time frames, and our ICE tables are going to help us work out those 2 different time frames. I stands for initial. So this is something not at equilibrium. C represents a change. So this is where we have equilibrium shifting, or we have a shift to achieve equilibrium. And then E stands for equilibrium. So we're going to try and fill this in with the information that we're given. It says the following gases were placed. Okay, when it says were placed, we're talking about initial conditions. So I'm going to take my 8.00 moles of N2 and I'm going to divide it by the 4.00 liters. That's going to give me my molarity. And I've got 10 moles of H2, again in that 4.0 liter container. So I have a 2.50 molarity solution of H2. Now, at the initial conditions, you'll notice it has not mentioned anything about the ammonia. We didn't put any of it in there to begin with. So we're going to go with the assumption that that starts out at 0. Now it says after equilibrium was achieved, 1.2 moles per liter of NH3 was found in the flask. So I'm going to put that in here as well. And now we're going to be looking at trying to calculate our changes so that we can fill in the rest of the chart. So I'm just going to switch colors here. You can notice I'm going to start with the ammonia because I have 2 pieces of information about that. If it started at 0 and it crept up to 1.2 moles per liter, that must have gone up by 1.20. And now as soon as I have one of the changes, I can calculate the changes in the rest of the table. So if this is going up, it's on the product side. That means that the reactants both must be going down. We're using them up to create that ammonia. So I'm going to put my negative symbols in there to start. And now we're going to use our mole ratios to try and figure out how much it's going down by. So I can use some stoichiometry to find that out. I've got 1.20 moles per liter of NH3 being produced. And I'm going to use up 1 mole of nitrogen for every 2 moles of NH3 that are being produced. So that tells me that the amount of nitrogen that's being used up is 0.60 moles per liter. So that's going to go down by 0.60. We can do the same sort of thing with the hydrogen. I can start with either one. I'm going to start with the NH3. And I've got 3 hydrogen, 3 H2 being produced for every 2 NH3 that are being used up. And I get 1.8. So that's going down by 1.80. Okay, switch up my color again. Now I can calculate my equilibrium. So I'm going to take 2.0 minus 0.6. That leaves me with 1.40 moles per liter at equilibrium of the nitrogen. 2.5 minus 1.8 leaves me with 0.7 of the hydrogen at equilibrium. And I've already got the ammonia at equilibrium. Last thing it's asking us to do is calculate the equilibrium constant, KEQ. So our KEQ value is equal to the products over reactants. Get pretty used to drawing this out by now. And we're going to substitute and solve. And I got my KEQ value equal to 3.00. We'll do the correct number of sig figs there, circle our final answer, and we're done with that problem. So we'll try that, some of the equilibrium problems like that. Some of these problems will also include things like the dilution formula. So if we're working with aqueous solutions, if we're mixing those two aqueous solutions together, you may also need to remember the dilution formula. So just a reminder that when you pour 2 aqueous solutions together, your volume is going to get bigger. And so all of those particles, all of those aqueous ions are going to be spaced out more. So we're going to use the formula C1V1 equals C2V2. We may need to use that in some of our calculations before we can put those molarities into our chart. So here's an example of a problem where we have a dilution taking place. It said equal volumes of 1.60 molar silver ions and 2.60 molar S2O3 ions are mixed. And at equilibrium, our concentration of AgS2O3 2 at equilibrium is 0.35 moles per liter. Complete the ice table and determine KEQ. Now, it's got that reminder in there. Whenever you mix aqueous solutions, there's a dilution effect. So it's going to double the solution's volume and half the concentration. So in this one, I don't actually need to use that C1V1 formula because it's kind of given us a really good hint right there. But it says equal volumes of 1.60 moles per liter Ag+. If I'm doubling the volume, that initial concentration is going to be 0.8. Initial concentration, 1.3. And I'm not starting with any of the product there, but it does tell me that at equilibrium, the concentration is 0.35. That one I don't need to divide by 2 because it actually tells me what the equilibrium concentration is. It doesn't tell me that it's being mixed in. So now we're going to complete the ice table and determine KEQ. So I'm looking at the one that's easiest to solve a change for. So I know that this product is going to go up by 0.35 moles per liter. And I've got a 1-to-1 ratio with the silver ion. So this is going to be going down by 0.35 moles per liter. I've got a 2 coefficient up here, so it's going to be used up twice as fast as the other is being produced. So I'm going to put negative 0.70. Again, you can do the stoichiometry if you like, if you're not quite comfortable with those values, but we can start to find some shortcuts that we can use in our work as well. And if I can double a number in my head, then I'm probably going to do it. So now we're going to solve for the equilibrium values. 0.8 minus 0.35 gives me an equilibrium concentration of 0.45. 1.3 minus 0.70 gives me an equilibrium concentration of 0.60. And now we can go and calculate KEQ. So we'll take our products over reactants. We'll substitute in all the values at equilibrium. So a reminder that it's only equilibrium values that go into this expression. Otherwise, we're calculating a trial KEQ, which can give us information about which way something will shift. But only if we're comparing it to the actual KEQ. So I get that KEQ value is 2.16. So we'll take some time in class, pause the video. There are some practice problems for you to try on page 130 and 131 of your workbooks. So take 15 minutes, see if you can try some of those practice problems. I'll pull up the kind of answer keys for these after, but try and work through them yourself so that you know if you've got a strong understanding of what's going on. Okay, so answer for problem 1 here, I got 3.00 as my KEQ. Again, we needed to figure out what the initial concentrations were in molarity, so I had to divide by the number of liters. After that, I could figure out how much change that I had going from the 0 to 1.2 in the ammonia, fill in the rest of the change, and then get those equilibrium concentrations. Equilibrium concentrations can then go into the KEQ expression and just solve for KEQ. Okay, with problem number 2, I got an answer of 2.2. So again, same sort of thing. These were the problems that we tried actually in the class as well. So I got 2.2 as the answer. Question 3 here is a little bit trickier. It says a sample of 6 grams of carbon is placed in a 1 liter flask containing 1.4 moles of O2. So with this one, you'll notice that I've scribbled out the carbon. And we scribble out the carbon because carbon is a solid, so it doesn't actually change in its concentration. However, it does get used up, and we can use how much of it was used for doing some stoichiometry. So the amount of carbon used, I can calculate what we started with minus what we finished with. So we used up 4.8 grams of that carbon. So now I'm going to use some stoichiometry. I want to figure out the change in one of those concentrations. So I want to figure out either the change in the oxygen or the change in the carbon monoxide. I'm going with oxygen. If you used carbon monoxide, that's fine. So we're going to take that 4.8 grams of carbon, and first thing that we do is convert it to moles so we can cross the mole bridge. Okay, so I'm using the molar mass of carbon. I cross the mole bridge. I've got 1 oxygen being used up for every 2 carbons. And then I find the molarity of that oxygen gas because I'm going to take divide by the 1 liter container. So I've got 0.20 moles per liter of oxygen. Now that's being used up because it's a reactant, so that's why it goes in my table as a negative sign. I'm going to use that value to then figure out how much carbon monoxide is being produced. So you can see that I've got a 2-to-1 ratio in the chart there, so I'm going to double the value, and it's being produced, so it gets positive. So now at equilibrium, I have 1.20 moles of oxygen, 0.40 moles per liter of carbon monoxide, and there's what my question asked. I didn't actually have to calculate KEQ. Oh, I did have to calculate KEQ. Sorry, it says it in the question. Well, we'll do KEQ equals products over reactants. So I'm going to just take my 0.40, we'll square that over the reactants, 1.20 to the first power. Again, I'm leaving out the carbon because it's a solid. And I get a final answer of 0.13 for that KEQ value. Okay, so that's how we do those category 2 problems. Now, judging on how well the rest of the class is doing with this, how comfortable everybody is, you may decide as a class to pause the video here and just work on some practice problems that are found after the notes in your handouts. If you're pretty comfortable with this, then you can go on to the next category of ice tables, which I'll start. Otherwise, we can leave it for Friday. Okay, category 3 ice tables. This time, we're asking to find the equilibrium concentrations from KEQ and an initial concentration, but we're not given any of the equilibrium concentrations. So we're going to try and do a little bit more with these. I like to call these IC tables because we're going to add a couple of rows to our ice table to make sense of all the information. So it says the following gases are injected into a flask. We've got some hydrogen, we have some fluorine, and we want to figure out what the concentration of that hydrogen fluoride, that hydrofluoric acid, will be at equilibrium. And you'll note that there is no dilution effect because when we inject those gases, we can increase the pressure of that system, but we're not actually changing the volume. So when we do this, we're going to write out an ice table again, but this time I'm going to write an IC table. And I'm just going to give myself a little bit more space. I'm going to rewrite it on the right-hand side of the page. So we're going to have some unknowns in this problem as we go through. We're going to be solving for x. So we're going to put a couple more rows in there just to allow us to do some more work. So it says initially we're injecting 1.20 moles of H2 into that 1 liter flask. So my initial concentration here is 1.20 divided by 1. So it is in here as 1.20. That hasn't changed, but we have converted it to a molarity. And I've got 1.20 moles per liter of the fluorine. Again, I'm dividing by that 1. If it was a 0.5 liter flask, that would change the numbers there. And it doesn't mention anything about the HF, so I'm going to put in 0. Now, we're not given any equilibrium values this time. We are given a KEQ, but there's no change that we can calculate right away. So we kind of have to be a little bit crafty about this, figuring out what's going to happen in this system. If I'm starting with H2 and F2, we know that this system is going to have to shift to the right. So we know that those reactants are going to be used up. And they're in a 1-to-1 ratio. So at the change, I'm going to show that these both go down by x. And the HF is going up by 2x because of that 2 coefficient. So at equilibrium, I'm going to have 1.20 minus x, 1.20 minus x, and this is going to be 2x. So you'll notice that our equilibrium, we don't actually have a concrete value yet. Now we're going to go over to the equilibrium expression. So I'm going to write out an equilibrium expression for this. KEQ equals HF squared, that coefficient becomes the power, times my concentration of hydrogen times the concentration of fluorine on the bottom. So we're going to substitute everything that we know in this equation. So I know my KEQ. I know that that concentration of HF is going to be 2x. And on the bottom, my concentration of H2 is 1.20 minus x, and F2 is also 1.20 minus x. I'm going to rewrite this. Now you'll notice that I have something multiplied by the same thing. So I'm going to rewrite this so that it's just squared. So I've got 2x, everything squared on the top, over 1.20 minus x squared on the bottom. So you'll notice I've got a squared on the top, squared on the bottom. The way to get rid of that squared is to square root everything. So I'm going to square root both sides. Square root of 2.5 is 1.58. Square root of 2x squared is 2x. Square root of 1.20 minus x squared is 1.20 minus x. So now I don't have to worry about those squareds. It makes my equation a lot neater. And what we're going to do is going to try and solve for x. So I'm going to bring all of this bottom part up. I'm going to multiply both sides by 1.20 minus x. So I've got 1.58 multiplied by 1.20 minus x equals 2x. When I multiply the right-hand side by 1.20 minus x, it just cancels out that term. I'm going to distribute the 1.58. So 1.58 times 1.20 gives me 1.89 minus 1.58x. So remember your distributive property, I like to call it the rainbow rule, equals 2x. We're going to collect like terms, so I'm going to move this 1.58x over to the right-hand side. So we're going to add 1.58x to both sides. So I have 1.89 is equal to 897x. You want to keep as many decimal places all the way through as you can, so don't erase them in your calculator. And then lastly, I want to get x by itself. Right now I've got 3.897 multiplied by x. The opposite of that is to divide. So I'm going to divide both sides by 3.897. And solving for x, I got x is equal to 0.48 moles per liter, or 485 moles per liter. So I'm going to take that x value now back to my ICEE table. So now instead of 1.20 minus x, I'm going to have 1.20 minus 0.485. 1.20 minus 0.485. And then 2 times 0.485. So I've got that extra row in my table just to do a little bit of calculations. And when I do that math, my equilibrium concentration of the hydrogen is 0.715. Fluorine, same thing, 0.715. And 0.970 for the concentration of that hydrogen fluoride. So it asks for the concentration of HF when equilibrium is achieved. We just solve for it. We're going to put a units in there, circle our answer, and then we are done. Okay, one more problem here. We'll try another ICEE table one. It says finding the concentration, the equilibrium concentration from KEQ and an initial value. We'll try one more problem here. So we've got a 3-liter flask this time. And it tells us the molarity of these different things at equilibrium, but we're adding some moles of HCl into the flask. So again, we're going to set this up. We're going to do an ICEE table because we have no values at equilibrium. So we're paying attention to the units. The 3-liter flask is containing the molarity. It's not moles. So I'm going to put 6.00 in for the H2, 6.00 in for the Cl2. Oh, this problem's a little bit trickier. Okay, so it says it contains those at equilibrium, and then we're adding an additional 15 moles of HCl. So that's an interesting one. We're going to start with 3.00, but then we're going to add that 15 moles in a 3-liter flask. 15 over 3, that's adding 5.00 moles per liter. So we're actually starting with 8.00 moles per liter of our HCl. So kind of an interesting scenario here. Now, another thing you'll notice about this question is we're not given a KEQ value. So that's why it's telling us what the concentrations of those gases are at equilibrium, because we can actually calculate the KEQ from those equilibrium values and then use it in our second part of our problem. So KEQ is equal to our products over reactants. So remember, when you're doing a KEQ calculation, you always have to have everything at equilibrium. And this system was at equilibrium before we added that additional 15 moles of hydrochloric acid. So I get a KEQ value of 0.25. Okay, with our changes now, we can either calculate a trial KEQ with our new values, or I can use my Le Chatelier's principle to predict which way the system is going to shift. Now, if I'm adding additional HCl, my system is going to shift away from that HCl. So I know my products are actually going to be going down. And they're going to be going down not just by X, but by 2X, whereas the reactants are going to be going up by X. Okay, and I got that 2X because of that 2 coefficient. So at equilibrium now, I have 6.00 plus X, 6.00 plus X, and 8.00 minus 2X. So we're going to use that equilibrium constant that we calculated already, and now we're going to try and solve for X. So my equilibrium constant, 0.25. Remember, the only thing that changes that equilibrium constant is temperature. We haven't changed the temperature of the system. On the bottom here, I have 6.00 plus X. I'm going to substitute that in for H2. I'm also substituting it in for Cl2, and the net result is it's going to be 6.00 plus X squared on the bottom. So I'm just going to write that as a squared. Makes it easier to see what we're going to do with this equation to solve for X. So I'm going to square root both sides. So I get half is equal to 8.00 minus 2X over 6.00 plus X. Okay, so we're going to attempt to solve this the same way as we did the last one. I'm going to multiply both sides by the denominator, 6.00 plus X. I'll distribute that 0.5. So I've got 3.0 plus 0.50x equals 8.00 minus 2x. Kind of running out of room here. I'm going to collect my like terms. So I'm going to bring all of the x's over to the left-hand side. I'm going to have 2.5x. I'm going to bring the 3 over to the other side. So I'm going to subtract 3 from both sides. Is equal to 5.0. And I got x is equal to 2.0. So we'll bring that value back up to our ICE table. I've got 6.00 plus 2.0. And my equilibrium concentrations, I got 8.00 moles per liter, 8.00 moles per liter, and 4.00 moles per liter. The one that we're asked to solve for is the concentration of Cl2. So I'll give that a highlight and make it easier for my teacher to mark it. So there you go. A little bit of math. Takes us about half a page to solve, but definitely within the realm of solvability at this point. So I've got some questions for you to try for yourself. If you can go to page 134. One of the things is on page 134, there is a question where we don't nicely have everything being that is going to solve itself by square rooting everything. I've got one that I've got a quadratic with. So skip question number 1 unless you're up for doing a quadratic little challenge. And take about 15 minutes. This is probably take us to the end of the period today. I'll show you the answers, and then we're going to save the rest for the next lesson. So question number 1 here says, in the lab, we've got some hydrochloric acid that is pumped into a 3-liter flask. So immediately I have to convert that to molarity. It's heated to 80 degrees Celsius. How many moles of Cl2 will be found in that flask after equilibrium is established? So you notice as I'm going through this problem, I kind of collect all of my like terms, but we end up with a x squared plus 0.36x minus 0.54. We end up with this quadratic equation. So I can throw it into my quadratic equation and get 2 values for x. I'm going to reject the negative value for x, that -0, because you can't get a negative concentration. So looking at my scenario here, I'm kind of filling out this chart the exact same way. At equilibrium, my final concentration of chlorine gas is 0.58. Question number 2 here, again, is a little bit tricky because I have to find a trial KEQ to figure out which way that equilibrium shifts. So we practiced trial KEQ in the past lesson to see which way equilibrium shifts. And you'll notice that when I throw in those initial concentrations to the trial KSP equation, I get 4.0, and I'm going to compare that to the actual KEQ. We know that the system is going to shift to take that 4.0 to 5.0, so I need to make more products, which tells me that I have to shift right. So that's why I'm going to assign the right-hand shift. I've got a positive value there for that hydrocyanic acid. I've got negatives for the hydrogen and the C2N2. All the rest of the question is solved the exact same way as what we did before. We're going to substitute the equilibrium values into our KSP expression. If you wrote out an extra e's for the IC table, perfect. And I get a final answer of 1.89 moles per liter. With question 3, this is similar to one of the ones that we did in class where we looked at needing to calculate our KEQ before we got started. So we have kind of this initial equilibrium. All of these can be used to calculate our KEQ. And then we're taking some of that HCl out. So that's going to shift our equilibrium. And I'm going to use Le Chatelier's principle this time to tell me that if I remove some of the HCl, my equilibrium is going to shift to the right. So even though we've removed HCl, the reason why that is a positive value is because I'm looking at what happens to the system after I've removed that HCl. So it's going to be positive. The other ones are going to be negative. Once I get that final equilibrium concentrations with the X's, I added a couple of extra rows to my chart and solved for that final equilibrium, which I got 7.33. So we'll stop there and look at the other things on Friday. And thanks for watching.